Okay, welcome friends. It's week 4 and this is Thursday, which means it's our final day of the week for class, and then we will get after some lab activities tomorrow. Just by way of reminder, PLC 4 is up and running, and we're going to get that done by Friday. Usual deal. Quiz style format done by midnight. I did check. It does look like it's up, so hopefully it's going good. Homework 2 is posted and ready to go. However, little announcement here. I am not getting through quite enough stuff, so I'm going to push the due date for that homework back. It was due Tuesday, and I think that we have not gotten through talking about reflection by interference. Interference due to reflection, which we'll talk about today. And also we need to cover thin films, and I'm not sure we'll get through enough of that today, and it feels a little crunched. So what we'll do is I'll push that homework back from Tuesday to Thursday of next week. Okay, so this will be instead of Tuesday, this is Thursday. That's going to be let's see, this one would be the 19th. So it'll be the 26th. And the quiz will also go along with that. All right. So the whole package is getting shifted back 2 days. Hopefully that'll be helpful in terms of getting you a little bit more time on the subjects. And I know we need a little bit of time, so I'm going to try and get that to work for us. So other than that, and of course we'll have lab on Friday. And the labs, I have almost finished grading most of them. I do need to finish a couple and ship them out. So I do apologize for the lateness on the lab grading, but those will be coming in, let's see, the next couple days. I'll finish those off. So we'll have that, we'll get that going, and it will be lenses this week and interference next week. So that's the administration stuff. If you have anything if you have anything to contact me on, just fire me an email on that. Question, go ahead.
Lab is due tomorrow on the 20th or next Friday.
Lab is due on the Monday after the lab.
Oh, okay. So this coming Monday.
I'm just doing the lab. I'll post the lab on the Friday, and it'll be there for you, and you can do it over the weekend or whenever. And then the thing is actually due on Monday by midnight.
Okay. Thank you very much.
Sure. So let's keep talking about interference, because we've got a couple of things left to do with that, and get through what we need to so that the homework problems seem a little bit more tractable. We find the one which one's the right one? Maybe that one. Okay, we're going to talk a little bit about interference, and I've told you already that we have a couple of different ways of getting interference between two waves. So we've talked about the double slit interference. Let me check this one. We've talked about the double slit interference in which the waves have a phase difference when they meet, right? Because that's ultimately what interference is. It's how are the waves, or should I say, where are the waves in their cycles when they hit each other? Okay, so that's what interference is. How do the waves attain a difference or no difference in the phase? One way is, as we've been talking about with the double slit experiment, the path length difference, right? If one just travels further than another, it goes a little bit extra in its cycle, and then it hits this one, and you say, okay, what kind of interference do I have when a wave that's doing this hits a wave that's doing this, right? That kind of thing. So we have the path length difference, and if you're talking about double slit experiment, That, for me, is the basic quantity to understand. I would say definitely be able to draw the double slit experiment picture, pick out this, where is it, actually show, yep, there it is, it's right there, right? Like I did with the ones we've been doing. Calculate it, okay? Actually write an expression for the path length difference, and then put the conditions on it, okay? If I'm looking for interference, or if I already know the interference, right? How many wavelengths are fitting into the path length difference? Is it constructive, in which case we have an integer number? Is it destructive, in which case we have an integer plus the extra half of the wavelengths? Okay, so between two waves, one way to get them out of phase with one another and to establish interference is the path length difference, all right? Another one we started talking about last time is the wavelength. I call this the wavelength reduction effect, okay? It's the idea that I take a beam of light exactly like, or say two beams of light exactly as I had in the double slit, okay? Like this, they're coming in. One of them passes through a material, its wavelength is reduced, it comes out of the material, and then you interfere it with another one that didn't go through the material, right? So that's what we're working on now. We left off with that. The last one we're going to do is reflection. What I call the reflection phase shift. And we'll hit that hopefully by the end of class today, and that we'll finish these off, and then we'll put them all together and see where we're at. Okay, so when it comes to these things, this is the double slit. This is the double slit is one of the reasons we talk about the double slit so extensively, because it's a great example of just this. Okay, wavelength reduction happens in materials with an index. And reflection, we'll talk about that later. But effectively, anytime there's a reflection, the wave flips over, and you get a phase shift from that. Okay, so we were talking about wavelength reduction. We had kind of devised a way of calculating it. So let's go from there. We were talking about this situation here, where I had a block of material in the path of the wave, right? So it's hitting like about there. Okay. Somehow I seem to have drawn it like we're gonna apparently end up with some type of constructive interference here, it looks like. But what we did was we defined the length of the block to be L, and we were concentrating on the bounds of the block, because everything outside the block, it's the same for both waves, right? The wavelength is the same here and here on the outside of the block. The wavelength here and here is the same on the outside of the block. So we don't need to worry about that. What we want to do is concentrate on where the wavelength is different, and it's within the bounds of the block itself. So if I'm interested in the number of extra wavelengths, or I should say the number of, that's what I'm saying, the number of extra wavelengths. Then I called that delta n, which is how many more did we get here than we had here. And what we found was that it was equal to n minus 1 times L divided by lambda naught, where lambda naught was the wavelength of the wave in air. And I think you can probably see that we can generalize this fairly easily, because 1 is the index for air. I called n the index for this material, and therefore we have a difference in the indices here. Now, suppose that we had two different materials which had in index, like suppose this wasn't air, suppose it had an index that was closer to something like, maybe it's closer to this, and I had an N1 and an N2. Okay, well then I've got an N2 and an N1 in here instead of N minus 1. And then L divided by lambda naught, okay, is just the number of wavelengths that we had in the distance L. All right, so this is the difference in the number of wavelengths that we have between the lower wave and the upper wave, and we'll just assume that we're going to have these come into to interfere with one another at the end of this. Okay. Okay, so let's go ahead and take a quick look at a situation here where I do have a block of some other index up here, as well as a block of a different index down here. So we're going to actually generalize this a little bit because this is the air, this is with air here, okay? And then let's calculate it and see what kind of interference we might be getting. All right, so we'll throw a couple of numbers in here and see what we can determine from looking at the results. All right, so let's suppose that we have a couple of different blocks and they both have different indices. Okay, so I'm going to get a situation here where I've got a block here and same length block here, but it's a different index. So we'll call this N2. Let's call this one N1. All right, and I'm going to have a wavelength whose wavelength, I'm going to have a wave whose wavelength I know in air. Okay, coming in here to both of these things. Like so. That seems a little weird. I don't know. Well, I tried to draw something. Now I got something that looks more like destructive interference, but we'll see how we do. Okay, so if we consider trying to write the number of wavelengths and then take a difference, okay, again, we're only concentrating on this section of the wave travels themselves because that's where all the change comes about. So what we're going to do is say that in that distance, okay, the wave that goes through N1 travels, let's say, well, maybe it's easier. Well, we can keep doing it this way. It travels N1 times L divided by lambda naught, because remember this, it's really, you know what, let me back up a step and just say how we got about this, just in case. This is L divided by lambda 1, but lambda 1 inside N1 is reduced. That's where the index comes from in the expression. Whoops. Yeah, we'll do it this way. Lambda naught divided by N1 in the denominator, like so. Oh, crud. Good thing I look at the screen every now and again, because I guess it's bright enough that we have some reflection. Okay, so we're going to go here, and we're going to go lambda 9 to N1, like so. Okay. All right. So the number of wavelengths traveled in the distance L in material 1 is this divided by that wavelength. It's L divided by the wavelength, but that wavelength is reduced by the index of refraction, and that's how we get the expression that looks more like this, right? Where we get N1 multiplying L divided by lambda naught, and I got to write this a little bit bigger. So L divided by lambda naught. Okay. Conversely, you can also see that had I taken lambda naught over here, And I say that, okay, well, the number of wavelengths, or maybe we could look at it this way. The number of wavelengths in L would be number times lambda, right? It's a certain number times lambda 1. And lambda 1 I can rewrite like this. And I can come to the same expression from an idea of looking at it like this. I can come to the same expression by looking at it that way. How many of these occur in that, right? So it's the same kind of idea. Obviously, I can do the same exact interpretation here for the N2 material, and that's the way we can generalize this expression, which I'll write just underneath it here, which is the difference now in the two wavelength numbers between 2 and 1. We can just suppose we're going to go this way with it, and it's going to be L divided by lambda naught, like so. It's just going to be the difference in the indices, whereby I had just N and 1 last time. I just have N2 and N1 now. So that's the slightly more general expression when we run through different materials with indices that are not 1. If we take some numbers and let's suppose that we're going to try and determine the actual number of wavelengths, and then we're going to try and interpret what does that number mean. Okay, so I want to start thinking about how many wavelengths difference is it. All right, so I cooked up an example here. Let's throw a couple of numbers into L and N and lambda, and we'll see if we can't calculate what delta N is. Of course, it'll be fairly straightforward, but let's suppose that we have a lambda naught in air of 500 nanometers. All right, that's a pretty pale green, but it'll be good enough. Oh, the sun's coming out. That little break in the rain. Okay, hopefully you're all safe out there. Big blustery night last night, so yeah, hopefully everything's okay and that your the roof of your structure did not blow off. Let's go with N2 and N1. Let's see, what did I want to do here? I want to do 1.5. Let's go 1.5 for N1 and 1.6 for N2. So they're pretty close, but not air. Okay, definitely not air. It's probably some type of glass. Let's suppose that the thickness of the glass is in the micron range, 8.5 millionths of a meter thick, so pretty small, but nonetheless, there's still going to be several thousand wavelengths, or several, well, no, not several thousand, a couple of different wavelengths, I guess we'll find out. When you're thinking about the nanometers to the microns, all right, well, get rid of this. Right, you're automatically thinking factor of 1,000, but that's a little too much because it's 500 nanometers. So it's a couple different. Let's calculate capital N. So we'll do, I just erased it from down here, but it's the difference in the indices, okay? It's N2 minus N1, L over lambda naught. And we're going to evaluate it with those numbers, okay? And that means I'm going to get a 1.6 minus a 1.5. Okay, there's my difference in the indices, and I'm going to divide one by the other here. So I'm going to get 8.5 10 to the minus 6. That's listed in meters. So I probably should change the 500 nanometers into meters. Or I could have alternately changed that into nanometers. Either way would work, I suppose. But let's just go ahead and just stick with meters in general. 500 times 10 to the minus 9. Like so. Okay. So now this looks like 0.1 multiplying 8.5 divided by 500, and that's multiplying 10 to the 3. All right, so notice a couple of things. Number one, no units involved. This is dimensionless because it's a number, okay? This is a I counted the wavelengths and there's this many and there's this many more, okay? So we've got a certain number which doesn't carry any dimension to it. All right, no units to that. Second thing, I do kind of some weird notations here sometimes, but don't worry about that. This looks like it's going to be, this is going to knock down that by a factor of 1, so this is going to be about 100, and that's 8 over 500. That's like, that's going to 100, that's going to take out these hundreds here. So this is going to be a number that's going to be in the range of about 1 to 2, it looks like. It's going to be something on the order of 8.5 divided by 5, right? Because I've got a 0.1, which makes this a 2, and I've got that 2 can go away with these hundreds here, so it's really just 8.5 over 5. And so that's a number that's, well, definitely not 2, but it's 1.6 or 7, so let me just see what I come up with here. I come up with 1.7. Okay, so that's the difference in the number of wavelengths. All right. Now, this is wonderful. It's great, but we need to make sure that we can interpret what this final number means. Okay, we have got to put some physics into this. Okay, great. So this is the number of wavelengths extra traveled by the wave in, I guess I drew these backwards. I got that one being the lower wavelength and that one being the higher wavelength. It should be the other way around. Okay, so mistake in my drawing there. It's the number of extra wavelengths that 2 traveled above 1. Now, a quick note about that. If you flip them around and you say, like I did, I put N2 being the lower index and N1 being the larger index. So if I flip these things around and I end up with a negative number, just take the absolute value of it, because the negative, all it does is reference which one is lower. Okay, so in this case, if I subtract 2 and 1 this way and I get a positive number, that means 2 traveled more than 1. If I get a negative number, it means 1 traveled more than 2. That's all. But we're interested in the magnitude. Okay, we're interested in the magnitude. The number, the sign of the number doesn't matter. Okay, this is 1.7. So what is this? This is 1.7. This is 1.7 extra wavelengths. So what kind of interference are we going to see if I combine these two waves? And I say, all right, well, I'm gonna shoot these two waves through these blocks. They're going to come together, and then they're going to interfere, and I'm going to see what? Am I going to see a bright spot? Am I going to see a dark spot? What am I looking at here? Okay. Well, let's try to think about it in the context of the double slit. So in the double slit, when we had the path length difference, we had the situation where if the path length difference was an integer multiple of wavelengths, we have construction. Okay? And the same thing would have to hold true here. If I had an integer number of integer multiple of wavelengths extra, well, then they're still coming out swimming in phase, right? They're still coming out going like this together. If there's an integer number, then we get that at the end. If there's an integer plus a half, that's when we get the destructive and we get this, okay? So what we have then is to look at the difference between, well, if this was 1, it would be constructive. If it was 2, it would be constructive, okay? 1 or 2 equals construction. Whereas 1.5 would be destructive. Okay, so these two are the extremes, right? I get the brightest possible thing if I'm 1 or 2 wavelengths off. If it's an integer multiple of wavelengths, it's the brightest possible. If it's 1.5, I get it's the darkest possible thing, right? Well, this is clearly in between these, right? It's clearly in between a constructive at 2 and a destructive at 1.5. In fact, it's slightly closer to the destructive. But is it completely destructive? No, because it's not 1.5, it's 1.7. that means there's some construction. It's just not completely 100% going like this, right? It's also not 100% going like this, okay? So it's like one of them's up, and then this one's going down, and then this one's down over here, and then it kind of goes up over here, and then it's just down, and then by the time, right? So they're off. They're off by about a quarter of a wavelength. Okay, well, 1.25 wavelengths, but the one doesn't really matter. So they're not in phase, but they're not completely out of phase, and they're not completely in phase. So we get a little bit of brightness here. All right, a little bit of brightness. That's what the extra wavelengths mean. Now, if we wanted to think about it in terms of sinusoids, okay, I don't know how well that's getting drawn, but okay, there we go. If I'm thinking about it as a sinusoid, right, a wavelength is this distance right here. So if it's off by 1.7 wavelengths, you can count if and if you wanted to start at 0, okay, well, a wavelength would go here and then it would go to there. So that's one wavelength. And then 2 wavelengths would be to here. Okay, so if this is the 0, this is 1, this is 2. 1.5, right, would be right in the middle here. There's 1.5. 1.75 would be about here. So 1.7 is somewhere in between these two dashed lines right here. So if we look at the actual phase that the waves, should I say the phase difference that the waves have between them, you could say, well, if it was 1 wavelength, they're off by 2 pi. Right? If they're off by 1 wavelength, it's 2 pi. But 2 pi and 0, as you know, are the same thing in sinusoidal terminology. If it was 2 wavelengths, well, it would have been 4 pi, but that's the same thing as 2 pi, and that's the same thing as 0. But it means this is why you get construction with 1 wavelength, 2 wavelength, 3 wavelengths. It's the same thing as having 2 sinusoids shifted by 2 pi, or 4 pi, or 6 pi, but they're still going like this, right, when they hit. Now, if it was 0.5, then that would have said, well, I've only got this half a wavelength, and now they're off by pi, right? If I'm at a half a wavelength, that's pi. That means that instead of going like this, which would be, well, going like this is 2 pi out of wavelength, right? 2 pi out of phase. 0.5 of a wavelength off is now we've got trough hitting peak, peak hitting trough, and that's a difference of pi radians in the phase. Same thing as 180 degrees. So this thing falls, this 0.7, right, is falling not at pi, and it's not at 2 pi, it's kind of close to 3 pi over 2, which is a 90-degree difference. It's a little less than that, okay? But this is the phase difference in terms of radians you can associate with the sinusoid, all right? How much of a difference is it between that one and that one? And you could say they're about, it's not 100% in this case, but it's about 90 degrees off, all right? They're about 3 pi over 2 off from one another. Okay, so hopefully that helps thinking about the phase of the waves when they interfere with one another. Now, notice one other thing. Had I come up with different numbers here, right? If instead of using this set of numbers, I come up with some other index, set of indices, some other length, blah, blah, blah. And instead of coming up with 1.7 when I do the calculation, suppose I come up with 1.3. What if delta n was equal to 1.3? What would that mean? What would that tell us? What kind of interference is that? Okay, well, we're going to go back to the sinusoid here, and we're going to say, okay, 1.3, that's not 1, but it's not 1.5. right? It's not 1 wavelength and it's not 1.5 wavelength. It's somewhere up in here, right? 1.25 wavelength would be at the peak here. So it's just a bit past that. Just like 1.7 was not at the peak here, it was just slightly before that. Okay? But notice what's interesting here. When you ask what kind of interference would I get, if I traveled an extra 1.7 wavelengths, I get some kind of interference which we determined was not fully constructive. It was not fully destructive. It was partially, right? It was partial. It wasn't as bright as the brightest spot, right? It was less bright than that because there is something going on, but it's not fully canceling each other out. But notice, it's the exact same thing here. There is some brightness. It's not fully destructive. It's not fully constructive. It's partial. Okay? And in fact, I'm going to motivate that this would be the exact same brightness as this. If I shone the same waves through this situation, and I got that, and I shine the same wave through slightly different index, whatever it would take to make the numbers work out to this, that would be the same brightness. Because it's not a quarter, it's a little past, which means it's down a little bit on the sinusoid. This was not a quarter, it hadn't reached that, which meant it was down a little bit on the sinusoid. Therefore, they're both 0.2 away from destruction, which means that they have the same intensity. Okay? If you think of, you could think of it as both of them are 0.2 away from a destructive situation, or they're both 0.3 away from a constructive situation. Okay? So you'll get the same intensity for that one as you will with that one when you interfere them over here. All righty? Cool. All right, fun times? I think that'll do. What I want to talk about now is the reflection. Okay, I want to talk about reflection because at a boundary, whenever there's a reflection off the boundary, which there's always a, right, you have a material of one index and then a material of another index. There's a boundary between those two materials. Whenever a light is incident on the boundary, it's going to experience phase shift. Okay, now the phase shift depends on what the relative index is of the material that it's bouncing off compared to the one that it was already in. All right, so let's take a look at that. And then after that, we'll put this all together and see how it looks. Oh, you know, I was going to do this one. I just don't know how this is going to work out for you folks due to the whole video situation here. But I got this thing here, and I thought maybe I could try this with you and see how it looks. All right. I mentioned this last time, in which we had two wheels, which would be which we could mark. Suppose, well, I can't mark these really. What happened to the tape? Oh, there's a bit of tape on that one. All right. Oh, there we go. There's the red dot over here. Okay, so I'll roll this one like this. Okay, like that. And there's a red dot right up here. Yeah, you can see that. We don't seem to have anything on this one of that same nature, but that is above one of these weights. Okay, so let's just assume we can do this. All right, so interference and waves is kind of like rolling wheels, okay, because ultimately a sinusoid, yes, it describes oscillating behavior, but the rolling and the rotation of a wheel is also a repeatable behavior. Right, it's in some sense wave-like, and you consider the position of the dot as it goes around. Where's my dot? There's my dot. Position of the dot as I spin the wheel is sinusoidal. Okay, so what I was telling you last time is that if I take these two wheels and I mark the spot, right? I've got the red dot here on this one, and I'm going to move this wheel here, so that it also has a weight on the top side here, okay? And I roll them, right, the same amount. It turns out then that the dot is going to have the same relationship with the other wheel as it always had the entire time, right? I'll be able to roll this forwards and backwards, and they'll experience no change in phase relative to one another. Okay? So what's a path length difference? Well, the path length difference is the situation in which this wheel rolls just a little bit further than that wheel. And so when I then compare and I say, oh, where's the red dot now? You'll notice, oh, wait a sec, the red dot's off. It's not at the same relative place as it was on this wheel. So for example, if I take this and I roll it backwards over here and you say, oh, look, where's my red dot? It's right there. But now when I'm comparing these two wheels, look, this one's not there. It should have been like that when it hit because the weights were on top, but now it's got this pattern here. So I'm comparing a situation here where I've got this, and they're not the same. Okay, so that's like having different points in your wavelength. You're at different points in the wave. Now, if I consider a situation like we just had where the wavelength is reduced, okay, what does that look like from a picture standpoint? Well, and this is definitely not going to work out super well, but that's like taking a smaller wheel, right? It's going to go a few more rotations in the same distance than this one's going to. All right, so I'm going to start them. They're going to go into the material, and all of a sudden that big wheel is going to become that small wheel, and it's going to go like this, and all of a sudden I've gone around more times with the wheel in the material than I did the wheel not in the material. Okay, so a little bit of visual for you. I don't know if that helps at all, but there you go. Something to think about, maybe. Okay, so if we consider reflection, let's do this now here. Let's consider reflection off a surface. This will be interference by reflection. So any boundary between materials with an index will result in a reflection phase shift for the electromagnetic wave. So let's just start by considering normal incidence, which means that I'm going to have trouble drawing it because I'm going to draw something coming straight in and then going straight out. And that means I'm going to draw waves right on top of each other. So I'm not going to draw them that way. But I'm going to draw them at an angle so we can see them. But we're assuming they're just coming in and going straight out. And I'm going to put this boundary down here so we can see it a little better. Okay, we've already spoken of refraction, which is what happens to the wave as it goes into the material. Okay, so here I've got an N1 and here I've got an N2. Maybe this is air and this is water. Okay, it's the surface of a lake. We've already talked about what happens when the light from air comes in here and then it bends and goes into the water. We've dealt with that. Snell's law will take care of that for us. But now let's consider what happens to the reflected wave as it bounces off the surface. What we find is that the incident wave here comes in, and suppose it hits the boundary at a peak. All right, I know I kind of maybe got that a little bit it's a little bit off, but let's go, all right, like that. It hits at about a peak, like that. What is then the reflected wave going to do? The reflected wave is going to get bounced off, and we already know that the angle is going to be the same. I mean, I'm talking about normal incidence, so this really shouldn't be a big deal, but okay. What does the reflected wave look like? Okay, now here's the issue. We have to know the relation of the index here in material 2 to the index of the material here in number 1. I said this was, for example, air and water. So let's just pretend that that's happening. This is air, so the index is 1. Let's say this is water, so the index is 1.33. Okay? If you know those numbers, great. If you don't, I don't care. It's just I happen to know them. We have to look at the index of the material that the light is reflecting off and compare it to the index of the material that the light was propagating in. And we find that if we are increasing the index, right? In other words, if N2 is greater than N1, as it is in this case here, okay, then what we're going to find is that the reflection carries a phase shift with it, okay? The reflection phase shift is then actually going to turn the light all the way around by 180 degrees. So reflected, now this is going to be if, and in this case it is, N2 is greater than N1, right? If N2 is greater than N1, which it is in this case, the material it could go into has a larger index, which means it's slower in speed than the material from which the light was incident. Now here I've got it just past the peak, which means I've got to flip it to just past the trough as it leaves. And we'll see if I can do that. So here's the trough. So it's going to go down here and leave. Like that. Just past the trough. I tried to draw a trough in here to give myself a head start. Something about like that. I'm not really happy with that. It should be a little bit more than that. It should be like the trough has just happened. So put it here. Like that. Something like that. Well, the point being here is that the phase shift is a full 180 degrees. In other words, it's a pi shift. It flips the wave by a half wavelength. All right, so the conditions on the reflection turn into, oops, my face here was. I'm going to put this back so I know not to write here. Perfect. Okay, so if N2 is greater than N1, then the outgoing reflected wave is, now this is why I talked a little bit about the sinusoids and the phase difference. You can cast this in a couple of different ways. The reflected wave is 180 degrees or pi radians or 1/2 of a wavelength different from the incident wave. Okay. The reflected wave is whatever it is, different from the incident wave. So my pen is running out a little bit. Switch to this one. Okay. All right. If it's not, in other words, if N2 is not greater than N1, what if it's less? What if it's a situation where the light had originated in the water and was coming this way and then reflected off and bounced back this way? Again, the refracted piece, when the light leaves the water, that's taken care of by Snell. That's all fine and good. But suppose we're just dealing with normal incidents here. I told you I was drawing them at an angle just so we could see them. But just think about the light coming straight down and then bouncing straight off, or the coming straight up and bouncing straight down. In that case, if the light is going water into air, in that case, the phase difference is not 180 degrees, it's 0. All right, so the other part to this is that if we go to the situation where N2 is less than N1, if I'm going from a larger index to a smaller index, then what happens is there is no phase shift. It's a 0 degree phase shift. Okay, the phase shift is 0. All right. So the reason that things like that happen kind of have to do with, well, they kind of have to do with the continuity of the electric field across a boundary. And so if you want to think of it mechanically, you can think of it this way. It kind of like it might be an easier way to visualize this. If you think of it mechanically, like a string wave or something, right? Where you have a string that then is attached to a heavy rope. Okay, that's like going from a high speed to a lower speed, right? So that's like going from a low index to a high index. Okay, what you'll find is that if I try to wave this light, thin rope, which is later on connected to a big heavy rope, what I'll find is if I make a pulse in the light rope, it's going to hit the heavy rope and then bounce back upside down from where it was. The reason being is because the heavy rope has more inertia than the light rope. So by the time the wave hits it and it's trying to go, hey, come on, come on, come on, the heavy rope just isn't really moving very much. And so because of that, it bounces off and is upside down. Whereas if I thought of it the other way, if I had the wave pulse sent in from the heavy rope and it was going towards the light rope has less inertia. So the heavy rope is, and the light rope goes, and it reacts right away. Right? So it's going to produce a back reflected wave, right? From immediately reacting to the push of the wave pulse. It's going to then react to that and send backwards in the heavy rope a wave pulse of the same orientation, right? If I think about it like making a wave pulse like this, I'm holding the rope like that and making a wave pulse, it's going to come back at me in the same way. All right, so that's the situation where the speeds go from lower to higher and we get 0 phase shift. Okay. Well, maybe that helps, maybe it doesn't, but nonetheless, that's the situation. So what I want to do is now take all 3 of these interferences and put them together. Okay? I want to put them all together. And we're going to examine a situation in which we have to assess all 3 of the interferences happening one at a time. Well, I mean, they're all happening, but we're going to assess them one at a time. Okay? So I'll give you this situation. And what we're going to do is we're going to take the same idea as we just did, right? I have a boundary between 2 materials with an index, and I'm actually going to make the material that the light's bouncing into, or the water that I just erased here, the water, I'm going to make that a really thin layer. Okay, so let's examine a thin layer of water, maybe like that much. Okay. Let's suppose we're examining. Let's make it something a little bit visualizable. So suppose this is like a water droplet on a piece of glass, right? And you've wetted the glass, right? You've poured water on the glass, and then you've tipped it, and then the water in the bulk of the water runs off, but then you pull the glass back to horizontal, and you can look and see that there's a little bit of water left on the top of the glass. That's what I want to talk about. I want to talk about that water layer and then glass underneath it. Okay, so we'll draw it this way. Okay, I'll put a big, thick piece of glass underneath it. Okay, there's glass. This will be a thin layer of water. Okay, and then in the top we'll have air. Okay. Now, we're going to have light incident from the air, just like we did before. It's going to hit the boundary between the air and the water. Some of it's going to get reflected. All right, so there's number one. There's a reflection phase shift there. Okay. Note what happens next. Some of the light refracts into the water, goes a little bit further, bounces off this boundary, and then comes out, which means it's traveled more than the first wave did, right? The first wave just came in, bounced off. But part of that wave, or part of the light that wave was part of, right? Some of it bounced off, some of it went in, but then bounced off this one and came out. That means that wave traveled further than the first piece, and therefore we've got a path length difference. And while we have a path length difference, we also have a wavelength reduction because it went from air to water. So in the water, the wavelength is reduced compared to what it was in air. So we have all three interferences happening not all at once, but they're all happening in this situation. Okay? This is not something it's not something I'm making up just so we can do this. This is a very well-known phenomenon, which you will probably, when I give you these visual clues, this is probably something you go, oh yeah, I've seen this. For example, whenever you have a thin layer of something on top of something else, and this could be oil on top of water, right? This could be the thickness of a soap bubble, right? When you're made the, I mean, if so, either you have kids or you used to be one, and perhaps at some point you dipped the little wand into the soap solution, right, and the bubbles come out. Nowadays, all you got to do is turn the switch, pour the liquid in, and it makes all the bubbles for you. I mean, what's the fun in that, except that you get this large volume of bubbles and everyone goes, oh, look, soap bubbles. Okay. Back in my day, we had to expend our own lung capacity in order to make the bubbles, not just have some fan do it for us. If you consider the thickness of that soap bubble, then it would be air, water, air. And when you look at those surfaces, what do you see? You see rainbows, right? You see swirling reds, blues, green, right? If you look at the surface of the soap bubble, now you got to look at it, right? Not just go, oh, look, bubbles. We have to be scientists and go, this is cool, but I want to look at what's going on. I see a pattern. And it's the same thing with oil on water, right? Whenever you have an oil puddle, a drop of oil on a puddle of water, you'll go, oh yeah, look at this, or gasoline, right? There's a little bit of something that floats on top of something else, right? Liquid-wise. You're going to see that there's the rainbow effect, right? You're going to see, oh, look, a rainbow. All right, what's it doing in there? This is where it comes from. You're getting the finger shaking. This is where it comes from. So this is not just something that we're making up. This is actually like, yeah, this is what's going on. We want to be able to describe the interaction of light when it hits a thin film on top of some thicker thing, right? Like a thin film of oil or a thin film of soap bubble, liquid water, something like that, all right? So the name of that is obviously thin film interference. Well, maybe not obviously, but after my tirade, perhaps it is obvious. So thin film interference. Okay, so this is why we see the rainbows on those in those situations. Okay, so for simplifying cases, right, we got to deal with a lot of stuff here. So I'm going to simplify this. We are, just like in the last example, we are considering normal incidence only, not coming in at an angle. All right, this is going to be normal incidence. And if I'm talking about light, I should say normally incident. Okay, I do not want to consider it coming in at an angle. However, I am going to draw it that way so that we can see the differences of the incoming and outgoing beams. All right, but in your mind, it's always straight in, straight out. Okay, it's going straight in, straight out. I'm not going to draw it that way. I'm going to always draw it at an angle, and you should too. But I just want you to remember straight in, straight out. That's going to simplify our job vastly. Wow, now it's blustery. We got some wind going now. I don't mind the rain. I mean, the rain is fine. If we had rain, I just don't like the wind. I'm figuring this out. I don't like the wind. All right, anyways, it's blowing stuff around. That's not cool, man. Let's take a look. I'm going to do the same thing. I'm not going to draw the waves anymore. Okay, I'm not going to actually draw the wavelengths. I'm just going to draw a beam. Okay. Remember, it's straight in, straight out. Sorry, I'm not drawing it that way. But you wouldn't be able to see anything if I did. Here it comes. It's going to hit here. Here's my incident light. Okay. Imagine that there's a wave on here. I'm not going to draw it. Well, I'll tell you what. I'll compromise. I'll give you. There it is. There's the wave. It's coming in. I'm not going to draw it at the boundary though. It's too hard to do that. Okay, we get reflection. Boom. Here's our first thing. It hits this boundary, and some of it comes off. Okay. I'm going to call this, say, R1. Reflected number 1. R1. Okay. We're going to look at beam number 2 before we assess any of the interference stuff. We're going to look at beam number 2. What does beam number 2 do? Beam number 2, I'm going to do this in red. Beam number 2 comes into the water. Whoa. Holy smokes. So beam number 2 comes into the water, bounces off the surface from water to glass, and leaves the water. Okay? Goes out that way. This is R2. Okay? The interference we are interested in is between these two waves. Okay? So I'll just draw those. Here you go. I'm going to draw right there. Right there. There's waves. Those are the two beams of light, or two waves of light that we are interested in interfering. We want to come up with conditions on the interference between those two that helps us try and explain why we are seeing the rainbow pattern. Okay. So in assessing the interference between these two waves, we have to hit the entire booklet here. Okay, because remember, ray 2 or wave 2 traveled extra distance. So there's a path length difference. There's a reflection phase shift here and here. We have to assess both of those. And when in the water, the wavelength was reduced. So we have to assess what happens during the time that this wave was in the water, and now how many wavelengths did it travel, and now it's leaving, where is it in its phase, and we have to add that to the path length difference and the reflection phase shifts. Okay, this sounds like an insurmountable task. Don't worry, we'll get through it. Stick with me. I'll show you how we do it. Okay. I'm erasing one of the things I'm about to apply. I'm gonna erase my little face again. Okay. All right, I'm erasing one of the things I'm about to apply, and that is, let's just start with the reflection phase shifts. Okay, let's start with the reflection phase shifts. That means that we need to know the index of air, water, and glass, and we need to know what are they all relative to one another. All right, so this was N1, so we'll call that 1. Here is water, 1.33. We'll go with glass here as 1.5. Now, a couple of words. What about the light that goes into the glass? What about the light that goes in here? We're not interested in that. Why not? Because our eye, we're looking at, our eye is up there. We're looking at this from up above, right? And so what's happening is the light's coming down, hitting the surfaces, and then coming back up, and we're looking at the interference between the two waves, reflected 1 and 2, that are coming off here. If it's going into the glass, we're not seeing it. So we're not interested in it. Okay, so that's number 1. The light down here, it's wonderful. I'm sure it's doing great things. It's just not part of what we're looking at. Okay. Number 2, there is refraction in here. Normal incidence only, right? That's straight in, straight out. So that means if I have a 0 degree, and if you want to use Snell's law to verify this, please do. A 0 degree incident angle, right? Because remember, we measure angles only from the normal. A 0 degree incident angle means a 0 degree refracted angle. It goes in exactly as it went, as it hit, right? Now, if it was an angle, okay, now we've got bending and stuff like that. But if it's straight in, straight back out. This is why we use normally incident. So we do not consider refraction here, any angle stuff, no Snell's law going on here. This is the simplifying part of what we're doing, okay? Another thing to think about, hey, what about this? There's a reflection downwards off here, right? Yes. Again, that's not light we're going to see, though, because we're up here looking this way. And if you go reflect off here, and then come out, what about that beam? That beam's probably pretty dim compared to this one. So we're trying to keep things simple. If it seems like you're going, well, here's the deal. I need you to assess the relative importance of things, okay? Do you want to talk about interference of 3 and 4 and 5 and 6 light waves? I think 2's enough. So if we have 2, we're good, okay? If we have more than that and you have to now do more assessment of the interference of these other ones, you're going too far, all right? So keep it simple. Let's start with the reflection. If I'm looking at the relative phase of R1, okay, what's the relative phase of R1? We just did this. So it's air to water, that's going to be flipped over by pi, right? So R1, let's just keep a table of the phase shifts, all right? So R1 is plus pi. Look at R2. R2 went from water to glass, but that's again an increase in the weight in the index. So it's going to also have a plus pi. R2 is also plus pi. So they both flipped over. Okay. What else does R2 carry with it? Well, it's going to carry a path length difference. Okay. It's going to carry a path length difference because it went into this and then came back out. So let's call the thickness of this thing, I don't know, let's call it like T for thickness. Let's call it T. Sometimes you'll see it as D or L or whatever. Well, let's just call it T. So this now has a phase shift of plus pi, it now has a path length difference of plus 2t. Because remember, it's normal incidence. It's in, that's 1. It's out, that's 2. And remember, we're not dealing with angles, okay? No angles. Number 3, while in the water, there was a wavelength reduction, okay? So there's something that we need to do that helps us count how many extra wavelengths were there because of the path length difference. But remember, the wavelength was reduced during the path length difference, so we have to account for that as well. All right, so now we have to say it also undergoes a lambda naught divided by n2 because of the wavelength reduction in n2. Okay, notice, at no point other than assessing for reflection phase shifts are we ever going to use n3 because we are not interested in the light in n3. We are only interested in n3's index because of the bouncing of the light off the boundary at n3. Okay, so otherwise we're never using this. Okay, everything is about what's going on with this one. Well, okay, not absolutely everything, but most things. All right, so R2 experiences all of the reflection, all of the interferences, the reflection, the path length difference, and the wavelength reduction. Okay, so we have to put all this together. So let's put it together. The reflection part is such that it kind of acts like a modifier. It's not going to show up mathematically, but it shows up as a condition, okay? Here's the way I think about it, and I kind of hesitate to let you in on this now, but I'm going to go ahead and do it. The first thing I look at when I'm doing these types of problems is the reflection phase shifts, as I have just done. So the first thing I'm looking at is what are these two things? Because that gets me into the mindset of what are these waves attempting to do? Now, let me back up and say the waves are not attempting to do anything. They have no sentience of their own, as far as we know. But I'm trying to think of it as what works for me. All right, so when I see a wave that's shifted by pi and another wave shifted by pi and they're trying to interfere, I think about, well, what are they doing? They were coming in like this, and what are they leaving as? Well, if they hit at a peak, they're both leaving at a trough, but they're still swimming together, right? This one shifted by a half wavelength, but so did that one, so they're still in phase. Okay, there's no interference yet. There's nothing going on, but I'm in the mindset of if I did nothing else, right? If these two things didn't exist, and I don't know how that would happen, but this is how I think about it. I told you, if these didn't exist, then those two waves would interfere constructively, right? Because all this one did was shift over by a half wavelength, and so did that one. And so now, instead of doing this, now they're just doing this, which is the exact same thing. All right. So for me, I'm looking at this going, well, that seems like they're going to construct. All right. If I get a pi here and a 0 here, then I'm thinking, oh, that's doing this, right? Now that's more inclined to be destructive. Does that mean that it's definitely going to be destructive? No, because we still have to assess all of these things, right? So at this point, I'm thinking construction. Is it going to end up that way? Maybe, maybe not, because we still have to assess these things, but that's my mindset, okay? So now I'm going to say, all right, what happens to the wave when it goes in and out? All right, so let's set this up. When I take the path length difference, all right, of 2t, all right, the path length difference. Let's look at it from a situation of the double slit experiment, okay? What did we say? we said the path length difference was essentially responsible for the interference because there was nothing else in the double slit experiment that could cause interference. Well, now we have other things, but hold on. Let's just assess the path length difference first. Just hold on. Let's suppose that we thought of the double slit experiment and we said, why can't we use that same conditioning here? Now, thinking of these two things coming out swimming in phase, what if it goes through a path length difference of 2 thicknesses? What would it take for them to come out swimming in phase? Would that not mean that the thickness had to be an integer multiple of wavelengths? Like if you considered like 1 wavelength in and 1 wavelength out, that would put the reflected wave, that would put R2 at a difference of 2 wavelengths behind R1, but that's going to be constructive because they're still going to swim in phase, right? So if the thickness of this thing is such that twice the thickness comes out to be an integer number of wavelengths, then they constructively interfere, right? And that's looking only at the path length difference, okay? Okay, if I had this be a half a wavelength, it would still work out because it goes half wavelength in, half wavelength out. That's a full wavelength. So a full wavelength is going to still put it constructive, okay? So let's think about the double slit conditions. If I think of the path length difference, the PLD is equal to 2T here, okay? Path length difference is 2T. If it's equal to an integer number of wavelengths, then it will come out constructively, right? Not necessarily. Because remember, we need to use these reflection phase shifts as modifiers. So what we have is basically the situation of, okay, here's the path length difference, and we need to assess how many wavelengths does it need to travel in order to give construction or destruction, all right? So we'll go back to the double slit and we'll say, okay, look, if it's equal to m lambda, then that's one situation. If it's m plus a half lambda, then that's another situation, all right? Now watch. So this thing could equal, and we don't know yet, m times lambda, just like it did in the double slit, m plus a half lambda. But let's be careful. What is the lambda? Oh, wait a minute. If I'm writing this down with a wavelength in it, I need to consider the wavelength reduction. Oh, all right. So that really means that I need to do lambda. I'm just going to put lambda n underneath those things to remind me that that's not lambda naught. That's lambda inside the water or inside whatever the thin film is here, okay? Okay, so let's convert it so that we do have lambda naught, right? What that means is I'm going to say this thing's equal to m times lambda naught divided by n2, or this is m plus a half. Uh-oh. Going off the board here. Can I squeeze it in just in the very end here? Lambda naught divided by n2. Did it make it? It didn't make it. Okay, well, it's lambda naught divided by n2. I'll write it slightly bigger this way. All right, maybe that helped. M plus a half, oh, it just barely squeezed it in there, okay? So now it's m plus a half lambda naught divided by n2. All right, so in either case, we're going to divide by the n2. Why don't we just move the n2 out from either one of those, and then I'm just going to put it into this expression over here, all right? So now I'm going to work with 2 times n2 times t on this side, just so I don't have to work with fractions on the right side. All right. This could equal m lambda, that's lambda naught now, m plus a half lambda naught. Okay. All right. Oh, good. I was below the thing, below the glare. So hopefully you can follow along with this. I know it seems like a lot, and it kind of is. But if you, just like with lenses and mirrors, take it step by step, okay, and break it down. Now, the question that we have at the end here is, okay, what kind of interference do we have? We were in the double slit experiment able to say, hold on, if it's off by a half a wavelength, we know that's destructive interference. If it's off by a multiple of a wavelength, we know that's constructive interference. But you cannot do that here, okay? You cannot jump to those conclusions here. It is very tempting to do so, but you must resist this temptation. Now, we go back. How do we choose? Okay, how do we choose? Is it an integer? And does that mean constructive? Is it m plus a half? Does that mean destructive? We don't know. What we have to do, remember, is go back to the phase shifts from the reflection. Those are the modifiers, okay? So I kind of think of these right away, and then I think of them again at the very end, because now they come in and they tell me what to do here. They tell me, these reflection phase shifts tell me that if they are the same, then construction happens with an integer multiple of wavelengths in the path length difference. Because they are the same, it tells me that an integer plus a half times the wavelength in the as a number of wavelengths in the path length difference will give me destructive interference. Why? Because when they came off, they were both in phase, right? They both experienced the same phase shift. Therefore, remember my mindset before was like they are tending towards construction. They're tending towards doing normal things, okay? So if this is the case and these are the same, then we can definitely write this is constructive, and we can definitely write this is destructive. And you'd say, so what? Who cares? Can't we write that anyway? No, you can't, because you have to look at what these are. Now, if this was a situation with the soap bubble film, okay, right? You blow the soap bubble with your own lung power and you create this bubble of your own. That means what's happened. This is no longer glass, this is air, because that's air inside the soap bubble. And now R1 goes from air to water, has a plus phase shift of pi. But R2, which is going water to air, has a zero phase shift. That means that in order to get construction, I have to get R2 to travel an extra half wavelength. And that means now that's the constructive condition. And that is the destructive condition. So I have to be careful when I label these things, because what I need to do is say constructive, destructive. This is only true if the two reflection phase shifts are equal. And if they're not, then this is not true. Oops, I'm way off here. Sorry. Let me rewrite that. Didn't pay attention to where I was. Sorry about that. Okay, we'll try that again over here. If the reflection phase shifts are the same, then you write it this way. That says if the reflection shifts are equal. Then I can write this. Oh, well, that points to the, okay, god dang it. Okay, then it points to this in the red, in the entire red brackets. If the reflection phase shifts are equal, then I can assess m lambda to be constructive and m plus a half lambda to be destructive. That means if the reflection phase shifts are not the same, I flip those, okay? So if this happens where I go air, water, air, then the reflection phase shifts are not the same, and I have to flip the constructive and destructive conditions. All right, so I'm going to do that to this side here, because I can see we're just about out of time here. And now I'm going to do m lambda naught and m plus a half lambda naught. All right, now this could be destructive. This would be constructive. And that's only if the two reflection phase shifts are different. Okay? All right, so what you do is you kind of use the same thinking as in the double slit experiment. You put the extra n in for the index for the wavelength reduction, and then you choose your condition based on the reflection phase shift. Okay, so is this constructive and destructive? You don't know until you examine these two things right here. Okay, so when I see that they're both the same, I'm immediately thinking it's kind of like the double slit. I'm going to get constructive, I'm going to get destructive exactly the same way as I normally would. When these two things are different, one's a pi and one's a 0, now I'm going to go to this side. I'm going to say, oh, in order to get it back into phase, I would need the extra half wavelength in order to get these things back into phase, because it bounced here, and it shifted it by a half wavelength. It shifted them. Okay, so thinking pi and 0, I have to go this way. If I see pi and pi, or if I see 0 and 0, which I don't know when that ever happens, I got to go this way. All right. Okay, but I think we're going to have to call it done there because I think I've probably exceeded my time limit for today. But nonetheless, we'll come back on Tuesday and we'll do some examples for this, which is kind of why I needed to postpone the homework so that we could do that and get a couple of problems done in class and give you a look-see at what this looks like when you're trying to attack a problem with it. All right. So takeaways from this. PLC for Friday, that's for me, that's tomorrow. I don't know when it is for you, but make sure you try to get the PLC in. Homework is pushed till Thursday of next week, which I think I got the date right, which hopefully is the 26th. It seems like it was because Friday the 13th was last Friday, so 20th, so today's the 19th, 26th, so hopefully that's right. Homework's next Thursday, quiz next Thursday, lab on Friday, and then you'll get to work on that over the weekend. In the absence of anything else, happy rest of your day. I hope that you stay safe and try to drive safely, because I'm just going to say it, you know, when bad weather hits, people drive like idiots. So try to avoid them and be safe. But you're taking an online class, which means you never have to leave the comfort of your own home. So congratulations on that. What a great choice. See you next time. I'm going to sign off from here, but I'll be ready to do the lab for you tomorrow. Take a look for that. See you later.